Related rates. What a wonderful topic we're going to embark upon today. We'll spend a few days on related rates. There's some good problems that we're going to see and some typical problems that we're going to see, and you'll probably see one on the AP exam as you take the AP test. So, critical information today. If two or more quantities are related, then their rates are going to change. The rates at which they change are going to be related as well. What does that mean? Well, let's give you an equation, y equals 3x plus 5. How are the rates of change of x and y related? So let's think about y equals 3x plus 5. And let's go back to our Algebra 1 days when we asked you to chart out what x values and y values we could have. So remember when we asked you to chart out that equation to graph it, we told you to go ahead and plug some numbers in for x. And we'll plug in 1 through 6. And you plug those in, you found your y value. If I plug in 1, we get 3 plus 5 gives us 8. If I plug in 2, we get 11. 3 gives us 14. 4 is 17. 5 gives us 20. And then 23 for 6. And then we were able to graph it. Well, what we'd like to do now, though, is to see, well, what happens as x changes. So if x were to change by 1 here, y changed by 3. And notice any time, it doesn't matter what x value we start at, if we start at 1 and go to the next, 3 to 4, change in 1, then the y changed by 3. So we can create another chart based on time and the change in those variables. So as x changes over time, so maybe this is 1 second, 2 seconds, 3 seconds, doesn't matter what it is. So as x changed by 1, y changed by 3. Well, notice now if we change by 2, what happens if we change by 2? So we go to 1 to 3, that's a change of 2. Now we go from 8 to 14. That changed by 6. And it doesn't matter, again, where we go. From 3 to 5, that changes by 2. And here we went from 14 to 6, or 14 to 20, which gave us 6. So as x changed by 2 over time, then y is going to change by 6 over time. What happens if we're at 3? So now we go from 1 to 4. There's our change in 4. And our y's change by 9. It doesn't matter, again, where we go, maybe 2 to 5. 2 to 5 is a change of 3. We would go from 11 to 20. That's also a change of 9. So we can see that we have a relationship between dx dt and dy dt. We can multiply our dx dt by 3, and it gives us our dy dt. Notice that if we take the derivative of y equals 3x plus 5 with respect to time now, so if you recall, we used to take the derivative of this with respect to x. If I take the derivative of y with respect to x, I get a dy dx equaled derivative of 3, which would be 3 dx dx, which we've talked about. We don't necessarily need that dx dx, and then plus 0. So dy dx was equal to 3. Now what we're going to do is do it with respect to time. So as y changes over time and as x changes over time. So the derivative of y with respect to time is dy dt. The derivative of 3x with respect to time is 3 dx dt. And the derivative of 5 with respect to time, again, a constant, derivative of any constant is going to be 0. So our derivative of y with respect to time is equal to 3 derivatives of x with respect to time. So if y equals 3x plus 5, then y will change at a rate of 3 times the rate of x. What importance does that give us? Well, if we know that maybe dx dt changed by 5, then I can go ahead and know that the y value is going to change at 3 times that x changing. So dy dt would change at a rate of 15. And it's going to be feet per second, feet per meter, or feet per minute or hour, whatever we want. So what we're going to ask you to do today, we're going to keep it fairly simple. We're going to give you a function or an equation. We're going to tell you some information about it, and we're going to ask you to find something else about it. So here, we're giving you the relation of y equals the square root of x. We're giving you dx dt, so x is changing with respect to time by a rate of 5. We want to find dy dt when x equals 9. So let's go ahead and find dy dt. So dy dt is going to equal, and now we take the derivative of the square root of x with respect to time. So we're going to have our 1/2 x to the negative 1/2, but we took the derivative of an x, so we get dx dt along with it. This is going to be the first time we're going to see that dx dt popping up. We did this with the implicit differentiation with the y's, because we took it with respect to x. Now we're taking it with respect to t. So you can think of this as more related rates, or related rates with implicit differentiation. Now we can go ahead and plug in what we know. We know dx dt equals 5. We also know that x equals 9. Oh, if I can write there. And we have our negative 1/2. Simplifying this, cleaning it up, that 9 to the negative 1/2 is going to be 1/3. We'll come off to the side here and talk about that, excuse me. We have 1 over 9 to the 1/2. 9 to the 1/2 is 3. Remember, negative exponents, take them to the bottom, or take it to the denominator if it's in the numerator. So we get 5 over 2, the 3 is coming down, so we get 5/6. So y is going to change with respect to time at a rate of 5/6. And that gives you an idea of where we're going to see this, and it's going to lead into much more bigger and better problems. So enjoy and good luck, and we'll see you next time.